Hello everyone, I'm doing this video with regards to our Math 241 final project. So my mathematical goal for this video is to enhance students' understanding of the relationship between a function and its derivative in relation to volume optimization problem by providing visual imagery of the problem. My pedagogical goal is that in classes where students perform optimization, a lot find that optimizing a function is hard to understand because they cannot actually visualize what is going on. A lot of times they just follow what they have been told to do, such as take the derivative of the function, set it equal to 0, find the critical values, and so on. And by looking at the graph of the function and the graph of the derivative together, they can actually see the relationship between the two graphs. During class, I would like to ask, why do we take the derivative of the function when optimizing volume, area, or other measurements? Why do we set the derivative of the function equal to 0? What happens when the derivative of the function is equal to 0? And using technology, I would like to create a dynamic environment where students can visualize the optimization problem, where one is given a square piece of cardboard where 4 squares are to be cut from the corners to be able to create a box. And the students are supposed to figure out what length of square cutout would give the maximum volume for the box. Here, the students can change the size of the cardboard and see the graph of the function and its derivative. The students can also tabulate the data and plot the points on the graph to see that it is the same as the graph of the function. This will let the students see the relationship between the function and the derivative, and would also be able to think of a way to recreate this environment for other types of optimization problems, like say instead of a square piece of cardboard, one is given a rectangular piece of cardboard. So I wish for the students to be able to recreate the same environment for other types of word problems like that. So to start it off, I would like to show you a picture of the square piece of cardboard right here, and I labeled the size of the cardboard as length, and then the length of the size of the cutouts to be x. And we want to cut out 4 squares from the side to create this box right here on the right. So the problem is that to determine the length of the edge of a cutout square, that will maximize the volume of the box when the side of the square cardboard is 10 inches. So for this particular problem, the very first thing that we have to do is to figure out what our function is going to be. This might be the hardest thing for students to do, but given the picture and given that our knowledge of volume for 3D objects like this is that we multiply the length, the width, and the height to find the volume. So for the length over here, we can see that this length right here is equal to the length minus 2 times x, right? Minus 2 times the length of the side of the cutout piece. So that's our length. For the width, it's going to be the same thing, which is length minus twice the length of the cutout piece. And then the height, which is this part right here, would just be the length of the cutout piece. So based on the picture, the students can actually see what's going on and why we're using that function as our reference for the problem. So the very first thing that I did in this problem is to tabulate some values regarding the volume and the size of the cutout. And based on this tabulated data, the students can see that the optimal or the maximum volume, which is about or approximately 74.04, is when the cutout length is 1.62 inches. And I graphed it and as you can see on the graph, that's about right here at this point right here. And that's just an estimate, because I believe the optimal size of the optimal volume is when the cutout is about 1.69 inches. Okay, so, and then I graphed the function, and the graph of the function overlaps with the tabulated data. So let's hide that graph right there in the table. And you can see this is the function right here. Okay, and then I want to show you the derivative of the function. This is the derivative of the function, and we can see that when the derivative of the function is equal to 0, which is at this point right here, that's the peak of the graph, which is the maximum of the graph. Okay, and this environment that I created right here is dynamic, such that you can change, let's say, the length of the sides of the cardboard to be 20 inches instead of 10 inches. And then we can see that for that, the derivative is 0 at about this point, which is right about here. So the length of the cutout piece should be at about 3.32 for the optimal volume. So this is yeah. And then for the volume, like I said earlier on the function, you can change this to fit other optimization problem where it's not a square cardboard. So just change or just create another parameter, let's say width, and then change this the value of one of the lengths to width or something like that. And I believe, given this as an example, students can actually visualize what is going on with the graph of the function, and also the graph of the derivative of the function, and why they have to set the derivative of the function equal to 0, and what it actually means as compared to the graph. Alright, so that completes the final project that I prepared for you guys. I hope you learned something from me, and I'll see you sometime. Thank you.